So today we'll be talking about communication systems. I'll start off by talking about wireless kind, and then we'll start with the wired kind. Bring the outer explorer. I guess after the workshops. Yeah, can you? Yeah. And like the Saley as well. So why is this? So yeah, wireless communications. So I'm gonna start off with asking some questions so you guys kind of get a context of why we're kind of talking about this. So say an aircraft is flying, right? How are we controlling usually? It's done through an RC controller. So how does that RC controller communicate to the plane? How do we control an autonomous aircraft? Is that any different than controlling a manual aircraft, right? Are there more components to it in terms of wireless communication? And there are, yes. So no matter what we do, we always want to have an RC controller for manual control, because no matter what you fly, there's always a chance of your autonomous software not working. So you always want to make sure while you're flying you have full control. What happens when the plane goes really farther than we can see? Can we still control it if it goes out of line of sight? What happens when a plane goes behind a hill? Right? You would think that would be fine, but radio waves penetrate the ground worse than air, right? So you might actually get interference. You might lose connection if you go behind it. What happens when the plane is far close to the ground? Again, something that you think might be fine, but radio waves can bounce off the ground and actually totally miss your plane. So that's actually what happened in the last competition, where a team was kind of flying too close to the ground for one of their objectives with a quadcopter, and they lost connection and they just crashed kind of further away. So these are things that RF is kind of like a bit of a black magic, wireless communications in general, because there's these kinds of edge cases they need to account for. So let's start talking about just the basics, right? So what do you need for wireless communication to work, right? So you need a transmitter and a receiver. You need something to send out some kind of electromagnetic signal and something to receive it, right? Sometimes you have both. So sometimes you want bidirectional communication between two devices, and those are called transceivers. So a transmitter sends out messages at a very specific frequency band, right? And then the receiver listens to that exact same frequency band. How many of you guys are in ECE or have like kind of some experience with what I'm talking about? Yeah. But basically, yeah, it's just an electromagnetic signal, and it has a very specific frequency band. So transmitters output power at a specific power output. So a transmitter, just think of it as a battery with a wire connected to it, and it charges the wire kind of like in an oscillatory fashion at the frequency that you want to transmit around. And then it does it at a certain power output. The higher the power output, the stronger the RF signal, the more range that you might get. So for example, the transmitters that we use here, they're like the most powerful ones are like 1 watt. You can't really go higher than that. The microwave that you use at home is 1,000 watts at about 1 gigahertz. So RF signals for communication, they don't need to be that powerful. You can still get a good range out regardless. And yeah, and receivers have, so transmitters have a property called what the power output is. Receivers have their sensitivity. So what is the lowest signal that they can listen to? So the receiver sensitivity is usually measured in dBm. So if you see something in dBm, then you know it's something to do with sensitivity. It's like a log scale. So something with 1 dBm has 1 milliwatt. It's like 1 milliwatt of power. If you see something, well, for example, in -70 dBm sensitivity, then you can measure a signal that's as small as 1 to the e to the 1 to the 10 to the -7 milliwatts. So these things can be very sensitive, and like your phone has a sensitivity of like -60 dBm, for example. So these are just terms that you might encounter if you kind of read the data sheet of this kind of stuff. and then you can get some more info on the link. So again, antennas. So what does it take to make a transmitter and receiver? It's an antenna on the transmitter. Like, where is it? It's all an antenna is just a wire. One that's on the transmitter and another that's on the receiver. This wire has to be a very specific length to transmit and receive a very specific frequency. The more precise the length, the more precise the frequency. And with any antenna, you might get kind of like a curve like this, where you're actually sensitive to a range of frequency bands rather than one very specific band. Yeah, and something important. So you guys might see different antennas, like longer ones, shorter ones. So the length determines the frequency, as I said. But the different kinds of antennas kind of have different properties called gain, right? So they can amplify a signal. And what they're really doing is redirecting the power output from your transmitter into a more specific direction. So this is what kind of like, I guess, a gain plot would look like for an antenna. So you can see on the sides, so that what the antenna is doing is it's redirecting all that power that would usually go in a circle and redirecting it to the sides so that it can reach longer ranges, right? So when you guys hear the term antenna gain, you're not actually creating more power. You're redirecting the power that you have into a more specific area. So, for example, if you have, say you buy an antenna, it claims it has 3 dBi gain, which is like your 10 gain over your transmitter. If your transmitter is only 100 milliwatts and you're comparing it with like a 1 watt transmitter, the 1 watt transmitter will always outperform, no matter what kind of antenna you have. So yeah, that's kind of an important point. And yeah, that's measured in dBi, kind of like dBm. With RF stuff, everything is done to the 10 log scale, so you always hear dBm and dBi when measuring performance of these. So let's just talk about the different types of antennas that you guys might encounter in the field. So, as I mentioned, a simple wire antenna is an actual antenna that you can actually buy. So, for example, this one out here. Some of them are sealed in plastic so that they don't deform or they don't get damaged while you're using them. And they have a uniform gain pattern when you're looking at it from the top, right? So when I'm controlling my plane, I don't really care kind of how I point my antenna, right? The other kind of antenna would be like a dipole. So those are like the T-shaped ones, and they have a slightly different pattern compared to the omnidirectional ones, and they're a little more omnidirectional. So these are kind of fairly commonly used when flying RC planes, and because you guys can see that the gain pattern drops kind of in the center, right? So if you're mounting a receiver or a transmitter antenna onto a plane, you would kind of want to make sure that this axis is on the parallel side of the plane, right? Because as it's flying, you can see that you're not going to get good reception when you're directly behind the plane, but you're going to get good reception no matter where else it is. But if you were to mount it like kind of perpendicular to the plane, then if you're like above, if the plane is like, if you're right below the plane, you might actually lose signal. So you don't have to know this that much, you just have to know the idea of a gain pattern affecting the placement of antennas on your vehicle, because that can actually affect things. So we use these ones for the plane. We don't use them for the quads, I believe. I think we just use a simple omnidirectional antenna for the quads. And then finally, this is like the Yagi antennas. And you guys might have seen this in the bay. This is what we use in the tracking antenna. Basically, they offer a very large gain at a very specific direction. Kind of, you deviate from that direction, you're going to lose performance, which is why we have to have something like the tracking antenna that constantly points towards the plane or where it's flying. And yeah, so if you guys are curious, refer to the data sheets for this kind of stuff in terms of what the radiation pattern looks like for the antenna that you're using. I think I have. But yeah, so a Yagi one I think looks like that. So at a very specific direction, you're going to get very good gain and reception in different directions. So at the front and the back, you're going to get the same kind of radiation pattern.
which is why you should never stand behind one the tracking antenna while it's operating. It should be okay, but best not to. Okay, so frequency bands. Not politics, but there's lots of regulation in this. So basically everything from 0 hertz to like 300 gigahertz has been licensed in some way. Some are, for example, reserved for TV, some for radio, some for military, cell phones. And like you can actually kind of take a look at the division of the frequency bands. This is, I think, just in Canada. But the reason kind of why we use particular frequencies when we're flying planes is because those are the frequencies that we're allowed to use. Everything else is kind of licensed to the military and so forth. So the ones that are popular, so the ones that are very commonly used in aerial robotics are 433 megahertz, 960, 2.4 gigahertz, which is the same frequency as Wi-Fi, and 5 gigahertz as well. And then the ones, so like very old radios used to operate on 75 megahertz or so. You can still buy RC controllers that operate on that frequency, but I don't think they're any longer used. When you buy RC radios, you can usually buy different frequency bands. So the lower you go, the better the range that you're going to get. Which I think we'll explain. Yeah. So why do you care about frequency? So the higher the frequency, the more bandwidth that you might get out of your system, right? So, for example, think about these sine waves, right? If they've been run for the same duration, and say each peak is like 1 bit of data, you can clearly see that the higher frequency bands can pack more data in at the same amount of time, right? So the higher frequency that you go, that's why Wi-Fi operates on 2.4 gigahertz and 5 gigahertz for like the high-speed Wi-Fi, right? The higher the bandwidth that you're going to be able to get. However, the higher frequency that you go, the lower the range, right? So the advantage of lower frequency systems would be the higher range that you might get. So for example, low frequency tends to go through walls better. If you're going to be flying in mountainous regions and you might hit a hill on your flight, you might want to go for a lower frequency system because it can penetrate through, it might be able to penetrate the ground better. And important to note, so low frequencies can go through some different mediums and not just air. So for example, sonar and water, right? That's why submarines use sonar, because that's one of the only frequencies that can penetrate through the medium. But apart from that, water basically eats electromagnetic waves for breakfast. No matter what you do, anything above kind of like 40 kilohertz, you're not going to be able to operate it. So this means that you have to be careful in bad weather conditions like rain, because you might get a reduced range out of your full RF system. So what does WARG use, right? So you guys can explore the bay after we're done, and you guys will see the following system. So as we've talked about, so we need an RC controller, right, to manually control the plane. It's just like a little joystick thing. And we always want to have it whether we're flying autonomous or not. So when you have an autonomous plane, what do you have apart from the RC controller? Well, you have sensors on your system. So you're going to get sensor data out of them. You also probably want to tell your plane where to go, right? So you want to send it waypoints. So you need some kind of telemetry system in place. You can put it on the same band as your RC system, but for redundancy, we actually use separate radios for it. So in our case, what we do is we use a 433 megahertz system, our RC controller for manual control of the aircraft. The 433 megahertz is the most long-range system, so no matter what happens, we should always have, once we lose, like, for example, these ones will still have manual control, which is what you want. We use a 960 megahertz system with the XVs for telemetry, so that sends us back sensor data, and then allows us to communicate with the autopilot, so give it your waypoints to go to and so forth. And then 2.4 gigahertz system for just our video feed, right? So we can kind of see, as we talked about, the lower the range, the lower the frequency, the higher the range, and then the higher the frequency, the more bandwidth, right? So our high bandwidth stuff is on the 2.4 gigahertz frequency. Then kind of the medium bandwidth stuff is on the 960, and then the low bandwidth stuff, but like the safety critical stuff, is on the lowest frequency for the maximum range. Yeah, let's talk about RC controllers. These things are pretty cool. But they kind of look complex, kind of a little bit intimidating. So, what do they actually do, right? Is there anything special about them? So, RC stands for radio control. They're basically fancy remotes, and some of them come with an embedded transmitter and receiver, right? So this antenna here, for example, connects to like a little transmitter inside this module. The ones that they come with, when you buy them, are usually 2.4 gigahertz, and they're usually good for just flying at a hobby level, just nearby, within line of sight. So there's a concept called channels with these things, right? And how you want to think about channels is think about this joystick. When you move that joystick, that's like a single level of control, and that's one channel, right? You also have this joystick, you also have all these buttons, right? And they're all kind of different levels of control, so you can control a separate thing with each channel. And these things usually come with 8 to 16 channels, so 8 to 16 things that you can control on your aircraft independently, right? It's kind of like parallel connection between you and your aircraft. And kind of the big names of RC controllers are Sky, which is what we have. We have the Trans, as well as one of their other RC controllers, and Spectrum, if you're interested in buying. Okay. So kind of keep the conversation going about what channels are. So when you hear something, for example, a transmitter outputs on 433 megahertz, it doesn't actually output at exactly 433 megahertz, right? The frequency, so you have a particular frequency band, and that's split up into however many ways you want in order to facilitate you sending out multiple channels at one time. So for example, say I buy a 433 megahertz transmitter, and I choose the frequency band to be ranged to be between 425 to 435 megahertz. And I want my RC controller supports 4 channels. So say I want throttle, I want roll, I want elevators, and I want yaw, right? All of those 4 channels. So what I might configure my transmitter to do is transmit so the throttle or the motor speed at exactly 425.00 megahertz, the pitch on 428, the yaw on 452, and the roll on 435, right? So I'm taking that frequency band and I'm splitting it up to facilitate multiple data streams at one time. And then I can control it, right? So each kind of channel is basically a separate signal line that a plane can listen to. More channels means more things to control. It also means more complexity, right? Usually when you're flying just a regular manual aircraft, you only need 4 channels. You don't need anything apart from this one, right? If you're flying an autonomous vehicle, you might need more, right? So I'll show you what we use for work. Yeah, and like they're usually very configurable, your RC controllers. You can like mix them and stuff, so you can be like, if I flip this switch and do something with this, it'll output something special on one of the channels. Say you have something going on with the autopilot, right? So for example, I move my throttle stick, which outputs to channel 1. The plane listens to 425 megahertz on the receiver, and then it speeds up or slows down the motor whenever it receives a change in the signal. You guys have any questions about how channels work so far? So what do we use at work, right? So I told you, you guys only need these 4 channels really for manual control. You don't need anything apart from that. So once you have an autopilot, things get a little more interesting. You might need more controls. So for example, you might have a 5th channel that's like a switch on your transmitter that changes between rate mode and angle mode, right? So in quadcopters, rate mode is if I move the throttle stick or the yaw stick forward, the quad will keep on flipping no matter what I do. It'll keep on going in that direction, keep on going flipping forward. And angle mode is like the throttle stick proportion is proportional to the angle that you want to be at exactly. So if I move the throttle or the yaw stick at like 12 degrees on my RC controller, the quadcopter should stop at 12 degrees and it should maintain a stable flight. You might also have an autopilot on-off switch, so if you want autonomous control or if you want just manual control. You might have a safety kill switch, which is a really important kind of thing when you're flying any autonomous system, right? So say your autopilot decides to rev up all the motors and your quadcopter or aircraft starts going out of control. You have a little kill switch that basically disables all output from the autopilot and going into the motors, and instead uses the ones from your controller directly. We've had this, and it lets the pilot control the aircraft in case of some kind of malfunction in the autopilot mode. And like you can have channels doing other more interesting things. Say the objective of your aircraft is to drop a ground vehicle for the competition. You can have a little channel for that on your controller so that you flip it, it'll drop. Yeah. So we talked about RC controllers. Let's talk about transmitters. What do they look like? Okay. Most can be configured with vendor software. So you guys saw me talk about kind of the frequency bands for the transmitter. So you would usually configure this beforehand through some kind of desktop software. Some have a nice USB input, like the Dragon Link, which we will talk about, and some you have to wire directly through UART, and then have a UART interpreter in the middle. Yeah, a transmitter and a receiver need to be binded or paired before, kind of like how you pair a Bluetooth phone. You need to pair the transmitter and receiver so that they know they're talking on the same frequency bands. Yeah, this is an important note in terms of safety. So say you go out of range of your radio, say you go behind a hill, say like you totally lose communication on your RC controller, right? There's usually a setting for that on the transmitter that you're using about what happens once you lose comms, right? So what do you want to happen? What do you want to just shut off all signals and have the motor stop entirely so that it just drops? Or do you want to do something else? Do you want to set a particular configuration of your channels so that, for example, the quad can go like a 0-degree angle and just slow down and fall into the ground? So this is the transmitter that we use at WARG. So there's an internal one in the actual transmitter, and then you can, or in the actual controller, and then you can actually attach one on the back, kind of like an external thing. So this is the Dragon Link UHF. It costs about $500, and it's a 433 megahertz system. We use this for competition flights. It's a really nice system. It's pretty configurable using their software, and it offers like 60-kilometer range if you want. This is the Orange RX. This is kind of like the precursor to the Dragon Link. It's a much cheaper system. It's only $45, and it's kind of like it uses open source firmware, which is nice. So it's even more configurable than the Dragon Link. It should offer decent range, but you only want to use this for test flights. So this you will also see this in the bay. And yeah, you'll cry less if you crash with this because it's a much cheaper system. It's not $500, but you'll cry more if you crash because of this. So definitely don't fly this with anything that's far range because your aircraft might have like $1,500 of components in them. So definitely don't rely on a $45 system if you're flying it kind of too far. And you can buy this at Logic as well with different frequency bands. And this is the last transmitter that you can find in our bay. We've used it in previous competitions and had some bad luck with these, unfortunately, so we don't really use them anymore. They're not very fun to configure. The software actually sucks, so in general, don't use it. Okay, so what happens when a ref just doesn't work, right? What happens when you get intermittent communication? So your throttle cuts off halfway and it keeps on cutting off throughout your flight. What happens if you think you have an error in a ref? So first, you can cry because these issues are really hard and really difficult to diagnose. Then you have to make sure that it's an actual RF issue, not something else. So make sure that it's not some software issue in your autopilot that's preventing proper communication. Maybe you have some kind of while loop that's just taking up too many resources or something, right? Then what you can do is analyze the RO spectrum. Mark, did you bring the spectrum analyzer? Yeah. Okay. So what a spectrum analyzer does is it lets you scan. It's kind of like a radio that lets you scan different frequencies in the environment, and it shows you. So this is what it looks like. We've got one at work. It shows you. It lets you know if there's a source of interference in your environment that can be affecting your communications. You can take a look at the arrangement of parts on the plane because a plane has electronic components that each generate their own kind of RF signal. If they're kind of nearby a transmitter or receiver on your plane, they can cause interference. So you have to take a look if there's any potential source of that in your actual plane. So for example, the power supply on an autopilot usually uses a switching supply, which means it turns on and off really super fast. And then that generates an RF signal, and if that's too close to, for example, your 433 megahertz receiver, and they're kind of like on the same multiple of a frequency band, then they can interfere and affect your communications. So we talk about this. So you can use, again, a special radio device is called the spectrum analyzer. It shows you different noise levels at different frequencies, so you kind of attach an antenna onto it, turn it on. Professional grade ones, depending on the frequency, can cost like tens of thousands of dollars. And yeah, you can take a look at like where the noise floor is at the different operating frequencies and so forth. So in terms of interference, if you have multiple signals at the same frequency band, that'll cause interference, right? So your receiver is going to be receiving things from multiple sources, and it might be confused. So that's why you want to make sure that the frequency bands that you use, that you can configure in your transmitter, are like clean before you fly. And this is kind of what the screen looks like. Right? So this is scanning from like 430 to 440 megahertz, and it shows you kind of a plot like this, right? So where you have the peaks are where there's a strong signal. And you can see that no matter what kind of signal you're going to send out, it's always going to be kind of a peak and then a little bit of a spread, right? Because transmitters and receivers can't transmit at an exact frequency ever. But this one can do, it's like a hobby grade one. You can do from 240 to 960 or 2.3 to 2.5 gigahertz, which is like basically everything that we use here. You always want to, so I'll talk about the antenna later on. Any receiver or transmitter you have, put the antenna on before you turn it on. The receivers are very sensitive to RF noise, and the transmitters, basically they're trying to output power on something that has no load, which is really bad for the actual circuitry. So you want to make sure whenever you have a transmitter or receiver, always put the antenna on, because it needs some kind of load to dissipate all the power that it's trying to transmit. With this particular guide, keep it away from powerful RF sources like the tracking antenna, because it's actually a pretty sensitive receiver. And yeah, as I said, never power the transmitter on or the receiver without an antenna. Usually the ones that we have are transceivers, so even though they're always transmitting basically. You can damage them that way. Cool. So let's talk about telemetry. What we talked about so far was the RC controller, which is what you use for manual control of the aircraft. What about telemetry, right? So these are XBs. These are pretty popular communication modules. Like usually if you search up hobby projects involving wireless communication, these always come up on smartphone and so forth. The low-grade ones that they always showcase operate on the 2.4 gigahertz band, and they're kind of low range, but they're easy to use. The ones that we use are like this version specifically is the XB S3B. They operate on the 960 megahertz band, so they got a higher range. They're pretty configurable, easy to use, and you can usually diagnose issues just by searching for them on Sample or something. And yeah, we use this for communication between the autopilot and the ground station, so communicating what the sensor data is reading so far, setting waypoints to the plane, and so forth. Yeah, so the specific ones that we use are the XB Pros S3B. They're the long-range kind of modules. Interfacing with them is done with UART, so it's a communication protocol, it's a wired communication protocol that Mark will be talking about later on. Usually, most of the telemetry radio systems that you buy, they usually communicate with UART. Yeah, that have some support with like swarm cell communications. So rather than having a single transmitter, like kind of having a single transmitter hub, they communicate with each other, kind of node to node, right? Most of the about are like master to node, right? So even if you have like 4 quadcopters, they would all have to talk to the same kind of master transmitter, right? But XP support swarm communication. So say you have like a line of quadcopters 500 meters away, or each one 500 meters away from each other, they can kind of communicate to each other until it relays back into the base system, so that can extend the range. So that's kind of cool, something cool about this. The ones that we're using, you should be able to get a 10-kilometer range outdoors. And they just kind of recently came out with 1-watt modules that have a really high range. I forgot what it is specifically, but it's more than 10 kilometers. So this is kind of the alternative telemetry radio system. So we talked about XBs. This is like the ski 3DR telemetry radios. If you search up the Autopilot or Pickops, this is kind of the system that they use the most on. It doesn't have as high of a range, but they operate on. But it's a lot easier to use when working with Autopilot or Pickops systems. They operate on the 433 or 960 megahertz band usually. I think the ones that we have operate on the 960 megahertz band. So basically 960 megahertz is all of our telemetry. We got a cheap side of these in the day that you can use for testing purposes. Although the XPs are good, better for competition flights. Finally, this shiny thing is the DJI Light Bridge. It's a 2.4 gigahertz based system used for transmitting our video feed. Right, so we've got a GoPro on our vehicle that connects to the receiver end of the DJI Light Bridge and then transmits video over to the transmitter end, or the end that connects to our computer vision computer. These are relatively expensive. They're about $1,000 for the whole system. We have 2 of these modules, one that we can use for backup. So the 2 smaller antennas that we use for the tracking antenna that you guys saw in the Yagi slide, 2 of those are for the 2.4 gigahertz band, right? And they're used to extend the range because I think the initial range of this might be like 2 kilometers, I think. But I think with the Yagis it's extended. Cool. I think that's it for me. You guys have any questions? The wireless comms?
Okay. So now on to wired communications. Right. So we have a bunch of sensors on the airplane. Tell us where we are, how quickly we're moving, what altitude we're in, and you have the autopilot. How do they communicate? Variety of communications. So there's that 4 wires there, many wires there. Why? Okay. Anyway, the GPS module for TikToks have a magnetometer in them and an actual GPS module. The magnetometer uses I2C, so this port, and the GPS uses UART, serial. That port will get into that. So, serial versus parallel. Has anyone seen parallel connectors or parallel lines recently?
Not recently, dude.
Okay, one. Basically, you're sending all of your data, so 80, 16, however many bits, all at once. So it's really fast, but you also need 8, 16, however many bits you're sending, that many individual conductors in order to send that information. Whereas with serial, you're sending 1 bit at a time, which means you only need, depending upon your protocol, 1 to 4 conductors. So you cut down on the actual physical layer that you need to have. The typical number is 2 to 4. There are some 1-wire serial protocols, but certain edge case. So again, it's a bit slower because you aren't able to send everything at once, but it's more robust because you can send of a semi-arbitrary length. Both ends need to know how long the data is that you're sending it, but you don't need to have an actual physical layer that is how big your data is. So, synchronous versus asynchronous. Why does it matter? So, synchronous uses a clock signal on one of the devices so that both of them know when to be looking for data. Asynchronous, the devices have to be looking on their receiving lines all the time to be able to see data coming in. And yes, so hardware-wise, asynchronous is easy to set up, but you have to be looking for it all the time. So, serial, or because we're technically incorrect, we call it UART. That's the actual physical circuitry that deals with serial communication. But yeah, so there are two data lines on this: transmit and receive on both devices. So as you can see here, transmit of one connected to the receive of the other. So there are three sections generally in the message for a UART communication. You have the start bit, you have the 8-bit message, and you have the stop bit. So normally the line is high, so whatever the high voltage is, 5 volt, 3.3 volts. To start the message, the sending device pulls it low, so 0. Then it sends its message, 8 bits, and then it pulls the line high again to indicate that the message has been sent. Optionally, there is a parity bit, which is essentially a rudimentary checksum, but it's not used on these devices. One downside of UART is it's, compared to other communication protocols, relatively slow. Yes?
How does parity bit work?
Basically, it has to do with whether or not the message is odd or even. If it's odd, it's high. If it's even, it's low. It's not used very often. You can more easily include a checksum somewhere else in your program. So, transmission needs to be known. The transmission speed needs to be known by both devices. Otherwise, one's going to be looking for signals at a higher rate than the other, and you're just going to get garbage. So, transmission rate is the baud rate, which is bits per second. Typical is 9600, so fairly slow compared to others. And the fastest you can reasonably get to is 1150. And that's pretty quick. Some smaller devices have difficulty reaching that speed. So, next option, I2C or I2C. Varies how people want to say. So this one, you'll notice, has 2 lines as well. But this one's synchronous, so it has a clock line. So the SDA, the data line, and the SCL, the clock line, both are connected with pull-up resistors. So by default, the line is high, and each device to send data pulls it low using internal MOSFETs. So that can be useful if you have a 3.3 volt device and a 5 volt device. You can run both lines on 3.3 volts and go on a 3 volt device. Also, it prevents overclocking. So when one master is pulled the line down, the other masters won't be able to send information over. Which gets to that actually should be on there. I missed that part. So one advantage of I2C is it can have multiple masters and multiple slaves, over 1,000 slaves. So you can have a lot of devices on a single I2C line. The way the data is sent, it pulls whatever masters you want to communicate at that time, pulls the data line below, and then starts the clock signal. At the edge of each clock for synchronous devices is when the data is sampled. So for I2C, there's two message types that are sent. The first one is the address, so which device am I talking to now? That's 7 bits in length for the actual address, and then 1 bit. Am I listening to this device or am I talking to the graphic? After that, you have your standard 8-bit message, and then more messages if you send them. And so these guys can go up to about 100 kilohertz frequency for sending data. The other synchronous data communication type that we use at WARG is SPI, or Serial Peripheral Interface. Is SPI. So it uses 3 data lines and a slave select line. So with SPI, you can only have 1 master, but you can have as many slaves as you want, in theory. So to communicate with each slave, you need a slave select line. So you either need a whole bunch of IOs for a whole bunch of slaves, or you can daisy chain through the slave devices. Also on here, you have the clock, so similar to I2C. But with this, only the master is able to command the clock signal. There's also OSI and BISO. So that stands for master out, slave in, and master in, slave out. So who's sending data, who's receiving data. By having the 2 data lines, it's capable of full duplex. So the master can send and receive data at the same time. That might get updated.
Sorry, maybe refreshing.
Just refresh it.
Cool. Alright, so to start communicating with a slave, the master pulls the slave line low, and that indicates to the slave that, hey, I'm going to be sending and receiving data now. So it sends out, the master sends out its data along with the clock signal, and then if it wants a response from the slave, it waits a specified amount of time, whatever the data sheet for that device says, and then it sends out another clock signal, and it receives data from the slave device. So with this, the length of the data being received from the slave needs to be known ahead of time, so that the master is able to send out a clock signal of appropriate length. Unlike with UART, where it can just be an arbitrary length, this needs to be known ahead of time. And as I was saying before, I2C and SPI have much higher data rates than UART. So 10 megahertz plus is substantially faster than 960 or 9600 bits per second. So that's nice. A variety of different communication protocols, but where do we use them? So for UART, it's our telemetry radios communicate primarily over them, as well as the GPS, and also programming them. Some of our chips can be programmed over serial. Our altimeter uses I2C. Is there anything else? That's the only thing I can think of.
I think maybe the airspeed sensor also used I2C.
Yes, so the airspeed sensor, we have two that we use. One's analog and one the I2C.
Yep.
And then for the IMU, which you need a lot of data from really, really quickly, that's what we use SPY for.
Yeah, with IME you can also do UART. So in general, when you're shopping around for sensors, they have a particular communication protocol that they use, and you can specify the version of a module that you want to use depending on the protocol that you want to use with it, right? So oftentimes the decision is yours, but sometimes it's also made for you. So some modules just only communicate on SPY, or some of them only communicate on UART, and you can't really do much about it, right? So that's why we have to kind of cover all of them, so you guys are aware of like what they all are.
So,
Yep.
It's not true. Going back to the previous slide.
Yep.
I2C versus SPI, your trade-off is flexibility versus data transfer rate.
so the
As in, like I2C, you can have multiple master slave setups, and SPI, you can have one master.
yes. So, and a bit more than that.
Okay.
So with SPY, you can only have one master. You can have a theoretically infinite number of slaves, but you need hardware for each slave. You need a slave line for each slave, so that limits the number. Whereas with I2C, you can have multiple masters and multiple slaves, and regardless of how many you have, you just have two lines. Hardware-wise, I2C is a little more complicated because you need the pull-up resistor and the open drain MOSFETs to hold the line low, whereas with SPY, it's just something out of whatever your device is. It just pulls the line high or low. And then the speed. So there are some, yeah.
So yeah, sorry, with SPY, an important thing to note is that the actual protocol can run almost at the same clock frequency as the chip that you're using, right? So say your chip is like 72 megahertz, you can theoretically run it that fast, although it's not good because of kind of range issues. But an important note is that you can also do full duplex communication, right? So as I send out a bit from the master to the slave can send out at the exact same time a bit from the slave to the master, right? So you don't have that in I2C. So the protocol in general can be extremely fast, and I can't remember what used it, but I think like an old computer part used it. I think it might have been like a CD drive, right? Something along those lines. That it was fast enough to use in like modern computing back in the day. Right? But I2C just has two wires across as many devices as one, which is nice.
Does that?
Yeah.
That's it? Okay, cool. Again, if you guys have any questions, feel free to ask them. So, everything doesn't work all the time. So, if you're getting garbage through a data line, or you're getting nothing discernible through a data line, you can use a logic analyzer. We have one. Basically, this little nice machine bit of aluminum connects in the probes, connect the probes to your data line and the ground, and then what it does is displays what's going on with each of the data lines. That's simple enough, but it can also tell you what communication protocols are being used, what the actual data in the message is, and it can give you entire groupings of messages. So as opposed to trying to look on a scope and capture that message being sent and figure out what that message is, you can just plug this in, it'll give you all the information right there, and then you can start troubleshooting a lot faster.
So for example, you can connect a UART line and you can see like what characters it's printing out, right? Like in the screen. It actually interprets the bits for you, so you don't have to do it yourself.
Yeah, it'll take the 8-bit message, convert it to ASCII, and then give you the ASCII character for the line.
Yeah, if you're sending ASCII.
Yeah. one last one is PWM. It's not a data communication protocol like what we were talking about previously. It can really only send one value at a time. The way it does it is as a percentage of the duty cycle or the frequency being sent. So how fast are these again?
So they're 20 milliseconds for a period, so up to 50 hertz is the standard PWM cycle, right? So 50 times a second.
Thank you. So the 50% duty cycle, or yeah, so that would be half the time is on, half the time is off. 75% would be 75% of the time on, 25% off. So a full would be full high, and a 0% would be full low. A lot of hobby components use PWM for communication. So the ESCs that we use for motors use PWM to determine how quickly they spin. So 0% would be off, 100% would be full throttle. And another note, these can, if you filter them, so it goes from a discrete high and low voltages to an actual analog voltage level. So you can simulate analog voltages using PWM. That's it.
So to add on to the PWM stuff, you guys might also see a variant of it called PPM. It's standing for pulse position modulation. Basically, it's like a more packed PWM signal that can carry 8 channels in one line compared to like 1 channel per line with a PWM signal, right?
And instead of varying the width, it varies where it's located within the duty cycle.
Yeah.
It's a bit odd in that way. It's not very nice to visualize, but basically it's similar to PWM, but carries more data.
And you guys might also hear, when doing embedded development, the term JTAG. So that's usually a communication protocol that's very specific to the processor that you're using, and it's something that the manufacturers use to test their chips before they're released to production, right? So it's like a very powerful protocol, but apart from programming the chip that you're using, you're not going to use it much apart from that. Basically, if you hear JTAG, it's usually if you want to program the chips, the microcontrollers that you're programming, you're not actually going to use it yourself to communicate, for example, to peripherals or anything. So you don't really need to know it.
And they're usually a derivative of SPI.
Yep. Yeah. Also, you can maybe use JTAG as a way to debug like the execution of your programs, I think sometimes. I'm not sure if that may be SW. That could be another protocol. But I think depending on the chip, you can also use JTAG for debugging. But yeah, it's not a communication protocol that you use with peripherals. But yeah, you guys might still hear about it.
Any questions about all this?
Have you guys ever done communication protocols before? Yeah, you don't need to know like the bit level stuff when working with these. You just need to know, usually there's support for them in kind of maybe the firmware or the hardware that you're using. It's more of making sure that the settings match up on the receiver and the transmitter, right? Just like as in the case of wireless transmission. So once you have everything synchronized in the same settings, it should be okay.
The main things to know are what communication protocol are you dealing with, and what do each of the lines mean, and how do I connect them to other devices.
Yeah. And basically, if you hear about any of these terms, you know it's a communication protocol. So that's also very cool. We finished early again. So. Oh, yeah. Wow. We need like 3 times more slides.
Yeah.
Yeah. Cool. Yeah. So feel free to come downstairs, check out the bay. I'll display the kind of the different transmitters, the RC controller. You guys can get a feel for it. And yeah, I guess that's it. Cool. Thank you.
Thank you for coming in.